So we want to talk about recursion. Okay, and let's start with writing recursive Fibonacci because that's the most obvious thing that we can write. Oops, sorry, Control S, fib.c. All right, so we're going to need a Fibonacci computation, and this returns will return an int, right? So we're going to say int fib of int n, and by this we're saying that this is a function that takes in an integer. This is the argument, an integer, and returns an integer, right? And once we do that, we will need to have a return statement. We're going to say if, so this is Fibonacci, if n less than equal to 1, return n, right? Return fib of n minus 1 plus fib n minus 2. Okay, so notice that very different from Python, we don't need the two branches because if this holds, then we exit here and we never execute the reminder, right? On the other hand, if this is false, we go here and execute. So the else keyword, I could write an else here, right? I would say else, right? Wouldn't make a difference though. And generally, Python programmers are very picky about the structure of their code. They want the code to be nice, readable. C coders, the general pattern is that they want to be very concise. The code can be tricky, can be subtle, right? They want to take advantage and optimize everything. So there's different cultures and different standards. Int main, and we're going to read a number. And let's declare the number first, n, and we're going to pass in the address of n, and we're going to print f and we're going to print n and fib n. So if we compile this, we say input 10, and we get the number, okay? And it's an exponential program, so if I'm going to input something like 20, it's going to take a bit longer, and let's make it take quite a lot longer. So let's say I say 50, right? You can see that it takes a while. Now, because we execute it in this manner, right? Maybe I made it too long. So one interesting command that you can use is time, and you're going to find out how long something takes. Now, because there's an input, we have to be very fast in inputting because that time will also be counted. So I'm just going to input 30 here, and then we get a report, right? Besides the output, right? We get a report. So this Fibonacci program ran for 0.01 seconds, right? And used 2% of CPU, right? And the total time between starting the code and stopping the code was 0.713 seconds, right? So let's try 40 because probably that's going to have to be very fast. And then you see that we have a total running time of 3 seconds, about 3 seconds, 2.922. And we're using 49% of CPU. Now, keep in mind that in the background, this machine is doing a video recording, right? And that hogs the CPU quite a bit. So we're not getting the full power of the CPU. All right. The other interesting problem that we solved was the towers of Hanoi. Okay, so let's try to solve that as well. Remember the problem. Has everybody seen it? Was everybody in the class last time? In the Python class? Right? So you can use the link to play it yourselves, right? So what we need to do is move all the disks to, and I did it the wrong way. Move all the disks to tower 3, right? But every move has to move a smaller disk on top of a larger disk, or you can go on a completely empty pole, right? So the solution here is based on the fact that so let's say I have a large number of disks. Let's say I have 7, right? Okay, which we won't finish, but right? Let me think of moving 6 disks, right? So when I think of moving 6 disks, this 7th disk that you see here doesn't really count, right? It's there, but if I decide never to move it, it's as if it didn't exist. Why? Because all the other disks are smaller, and any move on top of this pole will be valid, right? Worst come to worst, right? The only disk that remains here is the largest one because we agreed not to move it, and right, that's the largest one, so any move will be legal, right? So the recursion works in the following way. I can assume that I can solve the problem for a smaller number of disks. I can assume that I can solve it for 6, right? Now, I can assume that I can solve it for 6, so I take 6 disks and move them to power 3, but that will not be very useful, right? What would be even more useful is to generalize the problem. So instead of figuring out how to move from pole number 1 to pole number 3, I would like to move the pile of disks between any 2 poles, right? So interestingly, generalizing the problem makes it easier to solve. I don't want to solve it, right, by the original problem, which asked me to move all of this from pole 1 to pole 3, but rather from any source pole to any destination pole with using whatever remaining pole I have as an auxiliary pole. So if I have that problem, if I set out to solve that problem, now I can say, let me assume that I can move 6 disks from pole 1, from tower 1, to any other tower, and this time I'm going to want tower 2. Once I have performed that operation, right, because we assume that we can do, think of what we have. We have 6 disks on tower 2 and the 7th largest disk on tower 1, right? So at this point, it is perfectly legal to take this largest disk and move it from tower 1 to tower 3. And then I still know how to move 6 disks, right, from any source to any destination. So let us move them from tower 2 to tower 3. And again, we're going to have all legal moves, because while we're doing this, the 7th disk stays put. We never move it, right? So this gives us the strategy for solving this problem. Okay, so let's do towers of Hanoi. This is going to be a void function because all we do is print. And we're going to call it Hanoi. And we're going to have a number of disks, and we want to have a source, a intermediate auxiliary, which we call B, and a destination which we call C, right? And if n is 0, what do we do? How do we move 0 disks? Can we move 0 disks? Yes. I just stay like this and I move 0 disks, right? I just do this and I have moved 0 disks. Okay? So if n is 0, we could just return. We do nothing. Otherwise, we move n minus 1 disks from A to B, right? That was the solution. And then it remains that C, our original destination, is for the time being the auxiliary pole, right? Then we want to move the largest disk, right? So we're going to say we're not actually moving it. We're just going to instruct the user to move it. That's how our solution is going to be. So we're going to say move disk of size %d from pole %d to pole %d \n. And we have n here, and our current source is A, and our current destination is C, right? And then we want to move again Hanoi n minus 1 disks from where? B to C. So whatever is left is A, and that's going to be the intermediate pole, right? And this is the solution. Int main, and we're going to say again. So we can make it more interesting. So we can actually say input the number disks, and we're going to have a number of disks. And then we're going to notice that I'm not using a \n at the end. And then we're going to do Hanoi n. And then that's about it. And this is going to be Hanoi.c. So GCC minus O and Hanoi n, and we want to have 1, 2, 3, sorry, as arguments. Right? So input number of disks, so let's say 7. Okay, and then we have the solution, which is 2 to the power of 7, which is actually 128 moves. Okay, let's do it for fewer elements. So let's say we want 3, and then we get only 7 moves, right? And we can verify that this is the solution. Let me try to, right, we have the solution there. We want 3 disks, and we're moving pole disk of size 1 to pole 3, disk of size 2 to pole 2, disk of size 1 to pole 2, disk of size 3 to pole 3, disk of size 1 to pole 1, disk of size 2 to pole 3, disk of size 1 to pole 3, right? And this is the solution. So if we follow these instructions, we get a solution, okay? Now, the interesting thing that we could do is count the number of moves, right? How we argued sort of that the number would be exponential, right? And at this point, we're going to learn about global variables. So I'm going to declare a variable count and look at the place where we declare it. Okay, completely outside. And then with every move, so every time we do a printf, we're going to do count plus plus. Okay? And then we can print right at the end. All right, the number of moves, and that will give us the number of moves. And we should also say count here. So let's say we say 7 now, and let's see how many moves, right? 127. Okay? And then for verification, we can also say print f 2 to the power of n minus 1 equals %d. And how do we compute to the power of n minus 1? We don't have a power operator, but what we have to raise is 2, the number 2. So then what do we do? To the power of n. We learned a few lessons ago, right? This is the same as 2 to the power of n minus 1. This is to the power of n. Do you remember what it is? What it means? So the double less is shift to the left. We take all the bits, shift them to the left, right? So when we do that, every shift is multiplication by 2, equivalent to multiplication by 2. Right? Yes or no? Okay. So then we want to compute this value, and we want to reassure ourselves that we computed, we got the correct value. I should save. And again, let's say 7. And yeah, a backslash n has been put here. Okay. All right. So let's do yet another thing. Let's validate an arithmetic expression. So we are preparing for evaluating an expression. So in order to do that, let's analyze the structure of an expression. Okay? And we're looking for patterns here. So something like 1 plus 2 is an expression, right? An arithmetic expression. And when we see such an operation, a plus operation, right, these would be called what? Louder. Operands, that's a good name, but specifically for addition. So addition has two what? Multiplication has two what? Division has two what? So multiplication, addition has two terms, right? Multiplication has two factors, right? Okay, so they would be two terms, right? So, so I can say that an expression, and I'm going to use this symbol, which is actually a standard symbol in language theory, which says that a symbol of a grammar, we're actually defining a grammar now, right? Is defined as, and we want a pattern here. So we're saying that this is a term plus. So actually we could use minus as well, plus or minus. And you'd be tempted to say term here, right? But if I do this, 1 plus 2 plus 3, we are noticing that this is actually another expression, right? So we can say here expression, okay? But it may be solely a term, because this part could be missing completely, right? Now, instead of just 1, I could have 2 times 3 plus 4 times 5 plus 6 times 7, right? So now the terms are no longer numbers. This is a term, and this is a term, and this is a term, right? So what is a term? And by the way, I could have division. Right? So multiplication has two factors, right? So it's factor. It could be either, now it's true that division doesn't have factors. Division has, what was it called, right? So the second one is a quotient. The first one is a, I have to look it up. I can't remember. So again, yeah, something like that. But let's call them factors for simplicity. And again, we would be tempted to write factor here, but that wouldn't be good because I can actually have times 4, and this is another term, right? So I could say that this is factor term, and this part could be completely missing, right? So it might be just a factor. And now, what's a factor? Well, one thing it can be is any number. And I'm going to take a shortcut. I'm not going to want expressions of arbitrary numbers. I'm going to want expressions with single digits. This will make things a lot easier for us, right? But will nevertheless exhibit the same principle. So it can be 1, 1, actually 0, or 1, or 2, and this is supposed to be 0, or 1, or 2, right? Or, and so on, and so forth, up to 9. Okay? But guess what else can we do? We can do something like brackets, 1 plus 2. And inside here, I can have any expression, right? So a factor can just be bracket. So I'm just going to put them in, or maybe not. Let's just put them bracket and expression. Okay? So we're going to try to encode this into a program. Okay? I'm going to take it out of here. Okay, cool. And let's have a new piece of code which we call expression validation. All right. Now here we're going to apply a little trick. How do I know the difference between this and this? We have essentially two rules, two patterns there. How do I know when one applies and when to apply one and when to apply the other, right? Well, I'm going to take a sneak peek into the future input. Okay? So I'm going to take a sneak peek without actually reading it. I'm going to sort of read it and put it back. And if that input, that future input is either plus or minus, I know that this is the rule that should be applied. Otherwise, it's only this rule. Okay? So, in order to do that sneak peek, okay, we're going to read the string somewhere in memory. We won't be able to read one character at a time, right? Because of this look ahead, this is called a look ahead, we're going to read our input into a string. We're going to have a pointer that traverses the string one at a time. And obviously, when I need to do this, I'm just going to do star p plus 1, right? If it's equal to plus or minus, then I can apply this pattern instead of this pattern. It's going to be same here, right? So if I have a factor, how do I know whether I have a single factor or a factor followed by a star and another factor? I'm going to use the look ahead, and if I get a star or a slash, right, I'm going to apply the first pattern, otherwise the second. Okay? And here it's very easy because these are completely disjoint from this. Right? So I know exactly which rule applies. Okay? So we're going to write a set of recursive functions, each of them returning a Boolean. And actually, C doesn't have Boolean, so it's going to be ints, and false will be 0, and true will be 1. Okay? So we're going to start with int expression. And if we can validate the string, we're going to return true, otherwise we're going to return false. Okay? Now, again, outside, because of the recursion, outside of these functions, we have to declare our line. Char line, and we're going to use some length, so let's say 200. We don't want to use malloc. I mean, we could, but it's not a point here, what we're trying to learn. We don't want to complicate things too much. And we're going to use a pointer, p, that is going to be initialized with line, right? And is going to read characters from line. The terminator of the string is going to be \n. We're going to use f-get-s to read. So this expression, recursive expression, is going to advance p. Okay? Yeah, let's do that. So we're going to say if term, right? So we're trying to read a term, and if we have managed to read a term from the input, if we find a term in the input, we're going to return true, right? Otherwise, we're going to return false. Notice that the expression must begin with a term. If we don't get a term, then we return false, right? So if we return term, right, inside here, we want to take a sneak peek, right? So if star p plus 1 equal plus, or star p plus 1 equal minus, right? So if either of these applies, then we have a chance at using this rule, this pattern, right? But plus and minus would be followed by expression. So in that case, we return expression, right? So remember, this will try to read an expression from the line, which we're going to fill using fgetS later, right? So it's going to try to read. If it succeeds, then this entire sequence of parsing, this is a parser, this entire sequence of parsing succeeds. So the success of this entire expression depends on the success of this entire expression. This is what we're saying here. We're returning, right, the success of this. All right? Now, if this doesn't hold, right, then we must be here. And in that case, we have already succeeded, right? Because this guy has returned true already. So what we need to do is return 1. Okay? Does it make sense? Now notice that if we reach here, right? Either way, if we reach here, right, we will either execute this return or this return. So again, because of the returns, I don't need an else, right? I could put an else, but I don't need to bother. So what happens if this fails? If this returns false, then I should return 0. Okay? Does it make sense? Okay. So how about factor? Well, factor is so similar. I'm just gonna copy. And I'm gonna call this factor. Sorry, term. Right? This is factor. Return term. And I got the term function. And finally, factor. Again, there is something that I need to be doing here, right? So if p plus 1 equals to plus or minus, then I need to advance p. It means that I'm actually consuming the character. B, absolutely, yes, very good, very good. Absolutely, yes. And we need to do the same here. B plus plus. So let's focus on the factor now. Okay, so well, actually, I need to see. Just the last rule. I need to see it. So, right, we're going to look at the current character. If it's a digit, right, we can consume that character and return true, right? So if star p, and how do we check whether it's a digit? Well, remember that they are integers and they are in sequential order, right? So they're characters, but characters are integers, right? So if p is greater than 0 and the content of p is less than 9, then this is the digit, right? So what we can do here is p plus plus, and then return 1. Else, right? And again, we don't need the else because we have the return here. So otherwise, if star p is equal to open bracket, right? Equals to open bracket. Then we can consume the character, right? And what do we do next? We check whether this expression returns true, right? We are expecting an expression now. So if expression, but we can't just return the expression as we did previously, right? Because if expression is successful, I still have to check for the closing bracket, right? So if expression, then return, and actually I can't do that. I have to check if star p equals close bracket, and in that case I can do p plus plus and then return 1. Okay? If that doesn't happen, we have to return 0. Right? So we do have an expression, but the closing bracket is missing. That's an error. Right? Or the expression doesn't return true. Then it means that the expression is wrong. The overall expression is wrong, right? Or we don't have an open bracket. So at this point, what's happening? Well, this wasn't true, and this wasn't true. Otherwise, we wouldn't be here, right? So if neither do we have a digit, nor do we have an open bracket, then again, right, it's wrong. Okay? There is one more condition. Right at the end, we need to have a backslash n. So when we're done with the expression, the last thing has to be backslash n. Right? So where do we check that? We're going to check it in main. Okay? So we're going to say, what was there? F get S. I can't remember. Break lines, I think it was. Line N has to be N. Now we are doing not reverse lines, expression value. So f get s line, say 100. We're not going to be patient enough to input that expression 100 lines long. And then we do the following. If expression, so let's say expression returns true, right? Then I can say, and actually I'm going to take advantage of the fact that expression has completed and has consumed the expression in the input, right? So then I also want that star p should be equal to backslash n, right? Syntactically correct. All right. Else okay. So there's one more thing to do before we go. Did I put everything in the right place? Yes. So one situation we haven't encountered yet is this, where we use a function before it is declared. So it is used here, but declared only here. The C compiler is very stupid, and it's historically stupid, right? Because doing it in this way requires less memory. So it never looks forward for definitions. Okay? So what we need to do is declare the function before it is used. We provide what it is called a prototype. And the prototype is essentially this part right here. You can just cut and paste, copy and paste, Control C, Control V. And we need a semicolon. This is what is called a prototype. These files like stdio.h, and yesterday or the day before you saw stdlib.h, they contain prototypes. That's all they contain, right? So there are declarations. They are declarations for functions that are used before being defined. Where are they defined? They're defined in a library. We're going to look at that at some point, right? But I want to just reveal the mystery of these header files. Why do we use the angle brackets? Because there's a system folder where these files reside. We can use our own files. We can build our own prototype files and put them in the current directory. And in that case, instead of angle brackets, we would use just quotes. Okay. Okay, back to this. We also need a declaration for factor.
Wait. It's a class. Yes. Oh, I'm so sorry.
All right. So now all the functions are declared before being used. Okay. Now the definition itself counts as a declaration. So this expression function is fully defined here, but it is only used here. So this works fine, right? In recursion, it's also okay. It's also used here, right? But it's defined before being used. So that works fine. In recursion, also this use counts as coming after the declaration which happens here, right? So this works fine. So the only offending functions will be term and factor, which happen to be used before being defined. And notice the mutual recursion. There's a cycle, right? Expression calls term, terms call factor, factor calls expression. Because of this cycle, which we call mutual recursion, some function will be offending. That doesn't matter how we rearrange them, some function will be offending, right? And because of that, we will need to provide some prototypes. Okay? Providing all the prototypes is not wrong. So if I say expression here, it's actually considered good practice. Okay? So in the current case, the prototype of expression is not needed, but it's not wrong to have. Okay, so let's see how well we did. So let's start small. If I say 1, we get expression is syntactically correct. And it might be good to have some backslash n's. All right, let's do 1 plus 2. Expression is syntactically incorrect. Ooh. So let's try to figure out why. So the first thing I'm going to try is whether this is a problem. So I'm going to just delete this for a moment. Okay, so the problem is coming from the backslash n. So for the plus, we do have p plus plus. When I have the factor, the 0, I get a p plus plus, return 1. Okay, so let's do another thing. Star. Code of last chart character is 43. Not good. Last chart is plus. All right, so we're reading a term. So we're reading a term. The term reads a factor. The factor reads a digit. We do p plus 1, return 1. Come here. This should be false because we have a plus. And then we should return 1 because we have already succeeded. Then we return here. This should be true. So I do p++. So I'm curious whether this is happening. So it doesn't. After term. So this is how we debug. So after term we get plus. Which means that we don't need to have p+1 here. We can have just our p. Nobody caught me on that one. And should be the same here. Alright, so we can get rid of these. Alright, so now this is backslash n, right? The code for backslash n is 0. So let's clean up the code. Add back one plus 2, syntactically correct. If we say, for instance, something like 1 plus, incorrect. If we say something like just plus, incorrect. If we say, again, something like just 1, we get correct. Okay, so let's move on to 1 star 2. So this is correct. 1 plus 2 times 3, correct. 1 plus 2 times 3 plus 4, correct. Okay, let's start adding brackets. 1 plus 2, correct. If we miss a bracket, incorrect. Incorrect. 1 plus 2 times 3 plus 4 times 5 times another bracket. 1 plus 2 times 3 divided by 4 plus bracket 2 plus 3 close brackets, correct. If I miss a bracket, if I add one extra bracket, still incorrect. How many brackets to make it correct? One just, right? So now it's correct. So it kind of works, right? It's all fine. So let me explain this again. Is this part where's the other? I want to go to, okay, this one. Where are you here? Okay, so is this structure clear? Right? So again, an expression is either a term, single term, or a term plus minus another expression. Right? A term is a factor, star, multiplication, division, other term, or just a factor. And the factor is any digit or an expression within brackets. If we wanted to add power, let's say we want to add the caret as power, how would we add that? Very easy, right? So I'm gonna, how do we call them? So one is exponent, one is the base, and the other is the exponent, right? Right, but let's just call them both base. So we're going to have that a factor equals either a base to the power, I'm just going to write a base, but this is a huge abuse of language, but, or just a base, right? And then a base is this, right? So we insert essentially the exponentiation between, right? We insert the exponentiation between the multiplication and the single operand, right? So this part is clear, more or less, I'm hoping. So I'm going to go back here. And let's see again how this works with the code. I'm going to try to make this a little bit smaller so that we can see more of the code. So essentially, this expression is a function that consumes part of the input and consumes an expression from the input, right? And leaves the rest unchanged, right? So, maybe so then how are we going to use it in the main program? Well, we want to consume an expression, and we want that whatever is left to be the terminator of the string, the end of the string, right? So now if we go to the expression, we're going to apply the same principle to the term. So the term is a function that reads a term and leaves the rest unchanged. And if it manages to read the term, it returns true. If it doesn't manage to read the term, it returns false, right? So if we succeed, so we call term, and in the process of calling it, of executing it, the input advances, right? This P, which tells me which is the current element in the input, this P advances, right? Until the character immediately after the term. So we have read a term, we have advanced the P until after the term, and then we return true because we managed to read the term. If that's not possible, we return false. So let's say we do get true here, right? Which means we managed to read this term. There are two possibilities here. Either we have plus minus, right? In which case we are obliged to try to continue to advance the pointer, right? The current character, or not. So if it's not, which is the easy case, is a single term is already a valid expression. So if I manage to read a single term and I'm not followed, which is not followed by a plus and a minus, then I can very safely return true, return 1. The success of the expression is identical to the success of the term. However, if this guy is followed by plus or minus, right, then what do? I'm compelled, I'm obliged to go and read the next expression. I have to apply this pattern and go until the end, right? So I will consume one character, the plus or minus, whatever is here. I will consume it. It's there. I've seen it, so I'll consume it. And then I will continue reading another expression from my input. So I'm going to continue advancing this P inside the line until after the expression. And I'm going to leave the rest unchanged. And if I succeed that, if I get to this point, if this guy returns 1, right, I have to return the same 1. So essentially, the success of this expression becomes, at this point, identical to the success of this expression. Right? If this expression doesn't succeed, on the other hand, returns false, then I have to return false. So this return has to return the same thing as the value of the expression. So we might as well just return the expression. The truth or falsity of the expression should be the result of this other enclosing expression as well. Is this clear how it works? The same principle applies to term, right? Exactly the same principle, just that because the relationship between expression and term is the same as the relationship between term and factor. And if I go to the factor, right, things are a little bit easier here because everything is disjoint. So if the current character is a digit, success, right? It means that I can consume the current character and return 1. Or, right, if the current character is an open bracket, then I am compelled to apply this rule, right? So I have read the open bracket, so I have to advance my pointer. Then I'm going to try to read an expression. If I succeed, I'm still on a good path. I have a good chance to complete the factor. All right? So what do I need in order to fully succeed? I need that my current character to be a closed bracket. If that happens, I just read a closed bracket, so I have to advance my pointer, and I can return true. Right? So quite a few bad things can happen, right? One is expression might be, my current character might not be closed bracket. The closed bracket might be missing. Then this has succeeded, but this is not a closed bracket, false. Right? Or this doesn't succeed, false. Or I find myself here. What happens if I find myself here? Well, this was false. In order to reach here, this was false, and this was false. And what other possibilities do I have? None. There's nothing else I can be looking for. Therefore, false. Okay? All right, so I'm not going to start anything else because I'm not going to finish it. So next time, I want to return a tree that encodes an expression. we call it the syntax tree of the expression. So the only thing I'm going to do right now is introduce the console, right? So let's say I have a expression like this: 1 times 2 plus 3 times 4 plus 5 divided by 6. Right, the tree in question. So what's the last operator to be executed? Because we have precedence here, right? The last one is this plus. So we're going to come up with a tree where the last operation to be executed is at the top. Okay, and actually what I need is to make it quite large, right? Okay, let's see how that works. So what would be another operator to be executed before this plus? The star on the left, right? So the star on the left, and we would have 2 branches, and then we would have a 1 and a 2 here. Okay, now this guy would be executed just before this plus as well. So we put it here. Star. Oops. So let's draw 2 branches. And then like this. So I would have a 3 here, and then a plus, right? Does it make sense? And then we're going to have a 4 here, and division here. And finally, so now it's going to look weird. Let's use a star just to. And finally 5 and 6. So this tree, which we call the syntax tree of the expression, encodes very clearly the hierarchy of the operators, right? And then we're going to construct this tree, and we're going to evaluate it. And we're going to evaluate it with something that is called post-ordered traversal. Now, in order to construct it, we're going to use the program, the syntactic analyzer that we have built today. We're going to modify it so that instead of returning true or false, returns the tree. Okay, so returns the tree, or null if it cannot read a valid expression. Okay, questions? If you want to read 2 digits, we can use scanf, right? So the problem is advancing the pointer to the point where right after and that can be done. And actually we're going to try to do it next time. Okay? So one thing that C is very good for is writing compilers. And this is a first step in writing a compiler. And then one interesting thing to do, I'm getting ideas now, would be to generate the Python program that that evaluates the same expression. Okay, so we're gonna try to write a compiler. Questions? No? Class dismissed. Thanks for coming. See you next time.